Okay, at the moment you can see that I've got oscilloscope probes here connected to, let's bring the light in a little bit closer. These are the sample and hold circuits for the keyboard control voltages. So this is for KC1, KC2, KC3, KC4, 5, 6, 7, and 8. So it's these ones here that are for these 4 voices. So what I'm watching right now is this probe is going back to, he's going back to channel 1 on the scope. Probe 2 is watching the output of voice 1, and the same again for channel 3 and 4. Channel 3 is the sample and hold for the keyboard CV for voice 2, and channel 4 is the output of voice 2. So what I can see on the oscilloscope here is I've got all 4 of those measurements here. So this channel 1 shows the control voltage, and I've got a measurement set up for each channel here. 1 and 3, I'm taking the mean, which is basically measuring the DC voltage that's used for the control voltage. And the measurement for channel 2 and 4 is the frequency of the output. In this particular case, what I've done is I've turned off voices 3 and 4. The other thing I'll do is I'll just press the auto-tune button here. So these 2 voices have been quote auto-tuned. So voice 1, voice 2, let's see this again on here, voice 1 and voice 2. So now if we go for voice 1, we'll go up a tone, and voice 2 will go back down to C0. So it almost sounds closer like they're a semitone apart now. This is voice 1. I'm playing D flat 0. Now I'll play C0. So yeah, they're a little bit closer there. So I'll put it back into unison again. And we'll press C0 and sound them both at the same time. I'm going to hit C0. Now, right now, voice 2 looks like it's jumping around, but that's because I'm triggering off of channel 2. But, so now what I'll do is I'm going to do a capture a single sequence. Oh, a little bit too late here. Okay, so this auto arrangement is going to require a little bit of explanation because it looks pretty strange actually. When I have to hold down a key and I only have 2 hands to work with, but I need them both, I need something to make sure that the key's going to stay down. So I looked everywhere around my shop here for something that was heavy enough to hold down the weight of the key, and I couldn't find anything. It turns out I have this doll leg. Bit of a long story, but it was last Christmas at work we had a Secret Santa, and one of the guys that I work with, as a gag gift, there's a store called Active Surplus in Toronto, and they have a box full of these doll legs. So part of my present, he threw in this doll leg as the gag part of it, and the other part was a gift certificate for Active Surplus. So I've had this doll leg sitting in my shop for the last year and thinking, what the hell am I going to do with this thing? Well, of course, the other day I need something to hold down a key, and I look over and I think, perfect. I'll have this hold down. I put the multimeter on top of it, and voila. So I have an extra hand to help hold down a key when I need to do some tests, which is exactly what I need to do right now. So we'll turn up the volume so you can hear this. This is C0, and I want to capture just a single snapshot. There. So I'll turn down the volume again here on this because it's kind of annoying. What you see there is I've captured these two waveforms here. So you can see they're really not too different in frequency. The measurements that I have here, though, you can see that the control voltage, KCV1, is this line down here. That's channel 1, and that's negative 77.0 millivolts. And the channel 2, which is the output from voice 1, the frequency is 66.07 hertz. Channel 3, this is the control voltage, KCV2, for the keyboard control voltage for voice 2. That's this channel here. And it's negative 30.5 millivolts. And channel 4, which is the output of voice 2, its frequency is 71.53 hertz. So that's, when you hear that sound, it sounds really dissonant. It's because it's differing by, well, what's this? A little over 5 hertz difference, so that you can kind of hear the beat frequency in there. So what this is showing you, though, is that there's two different control voltages going to those voices. Now, I'm sure if we moved the probe and we looked at the sample and hold circuit for voice 3 versus voice 2, and we were to compare voice 1 and voice 3, these two might be a little bit closer, and I'm certain that these two frequencies would be probably identical, if not very close, because the instrument is tuned. So what this is telling me is that the voltage coming out of the multiplexer and going into the sample and hold, or coming out of the sample and hold circuit, actually, they're different. They're different control voltages. Now, that could be for a couple of different reasons, but this is where it gets into the hairiness of how the auto-tune works. So we'll take a quick step through this, and we'll talk about a couple of things. So each of these voices has a whole bunch of control voltages that come into them, but in particular there are two that are controlled by this keyboard. That's KCV1 is to the control voltage from the keyboard for voice 1, and that sets the pitch for what note you're playing, and that controls the two oscillators on this board. Now there are two additional control voltages that are setting the frequency for the oscillator, and that's basically what's controlled by this knob and this knob here. There's another signal that comes in here, which is a control voltage from the low frequency oscillator, and there's a couple more, but basically the main one that really sets the pitch of what's to be played and what ultimately is, where these are all going to sound the same when you're pressing the same note, is that KCV. Now, the other thing, though, is on this connector right here, and there are two signals that come in here, and what they're for, and this plays into with the auto tune, is when you press the auto tune button. So I'll turn voices 3 and 4 back on here. That's what this switch is for. So you can enable and disable voices. You can see that 5, 6, 7, and 8 are turned off because this particular instrument only has 4 voices. If we had the additional daughter board and 4 other voices, then we could switch all of those on. Now, what I'm going to do is, you can see the auto tune button here. I know it's kind of dark, but when I press it, it lights up. And what you'll see is when I press the auto tune button, each of those voices is stepped through in sequence. And what happens is the processor sends a control voltage in sequence to each one of these voices. What happens next is that this connector here is the output of the voice. all of these go back to here. Now there's actually two places where audio signals come out of here. There's one where all of the voices are mixed together and you get a multiplexed output that is for feeding back over to the processor board here. The other outputs are for what basically goes to these audio outputs here and goes through the pan pos to set the panning between the left and right channels. And then there's an additional piece that there's a voltage controlled amplifier on here, so that when you press the auto tune button, I'll put the doll foot on here so you can hear a note being played. Turn up the volume here. So you can see voice 1 is playing. Now if I hit the auto tune button, notice what happens. It goes quiet and comes back. So what happens there is when the processor is auto tuning the instrument, it disables the output by basically turning down the gain on a voltage controlled amplifier for the two line level outputs for the left and right channels. At the same time, that multiplexed audio signal goes back to the processor board here, and what happens is that as it steps through each of these voices, it produces a square wave of a very specific frequency. The frequency of that signal is measured here and compared in the processor and determine whether the output of that particular voice is sharp or flat. So if it's flat, then what it does is it adjusts for that by adding, and this is where these connectors here come in. There's two tuning signals. There's FT1A for this voice and 1B, FT2A 2B, FT3A 3B, FT4A 4B, and those are tuning coefficients. So and the reason why there's two of them here is because each voice has two oscillators. So it's tuning each oscillator, making it either sharper or flatter, so that when it's finished tuning them all, assuming the auto tune works successfully, each of these voices will be more or less fairly closely in tune with one another. And so that's where these additional two control voltages play in, where ultimately what happens is you've got a voltage controlled oscillator, two of them, and there's a summing circuit, which that might actually be what this 741's here for, but it uses an op amp and a set of resistors to control the weights of each of the inputs. But it's summing the tuning coefficient, the control voltage from the keyboard, the control voltage from the low frequency oscillator, the control voltage from the frequency settings here for the oscillator. And in certain cases with oscillator 1, you also have the ability to feed back the signal from the triangle wave from oscillator 2, feed it back into the input to VCO1 for cross modulation. And there may be one or two other voltages that I'm leaving out here. But basically you've got a number of control voltages that are all being added together ultimately to control the frequency of each of these VCOs. But what's of importance in this case is these two here, the tuning coefficients, because what our problem is that, turn up the volume again, sounds awful. That's a rundown on how the tuning circuit, I guess how the entire feedback loop works, and kind of the theory on how it's supposed to work, and a practical example of what happens when it doesn't work.